No, because I need to.
Okay.
Welcome for the last and final summer series. Thank you for joining us tonight. And I'd like to welcome Molly Carlson. Molly O'Guinness Carlson is a fellow level member of the American Institute of Advancement in Conservation and its associated foundation, AIC, FAIC, and has been a practicing conservator since 1990. After her master's degree, she worked at the Canadian Conservation Institute in Ottawa and with Dr. David Grattan as a conservation science intern. She took a position in the fall of 1990 at the Spring Point Museum in South Portland as the conservator of Snow Squall, America's last surviving extreme clipper ship. Molly opened her own laboratory in 2001 and reformed it as Head Tide's Archaeological Conservation Laboratory, LLC, in 2016. Molly has a special fondness for wet site and coastal terrestrial object conservation projects, such as objects from Etah, Greenland, Boom Island, and Malaga Island. Molly also worked with fine art object conservation for museums, historical societies, and private clients. Molly is the honored mother of 2 adult children and is also a national board certified high school special education teacher. Her hobbies include gardening, beekeeping, playing the fiddle in a Celtic band, and perfecting the art of brewing beer. Please welcome Molly Carlson. Thank you.
Thank you for coming out to hear my little talk tonight. This is on the conservation of the 1607 Fort St. George artifacts. And just to set some context, I know everybody in this room knows what the Fort St. George colony is, but for those out in cyberspace, I want to use some names that are very familiar to you from history. King Henry VIII, he had a daughter named Elizabeth I, and she died in 1603. And our native shore, Virginia, was named for her, the Virgin Queen. She was succeeded by James I, and he decided to grant the Virginia Company charters to exclusively settle Virginia, which in that time period was basically anything in the New World, Chesapeake Bay forward that wasn't Spain or owned by France. The charter granted land to 2 branches of the company, and the London branch established a colony near Chesapeake Bay, which turned into James Fort, which you would know as Jamestown, established in May of 1607 on native Algonquin-speaking lands of the Powhatan Indians, whose very famous daughter you would know as Pocahontas. The Plymouth branch was to establish a colony in New England, and this colony became our Fort St. George, now known in Phippsburg, Maine, established in August of 1607 on native Abenaki ancestral lands. There's a really unique item that goes along with the Fort St. George story, and that's this map, which was drawn by John Hunt back in 1607. And it's pretty rare to have documentation like this of a site. So this was a very exciting thing for the archaeologists to work with in order to locate the storeroom and do some work, of which I can't really go into, or else we would spend all day talking about just this map. I want to read this one quote to you. It's from a Smithsonian Magazine 2004 article that just describes a little bit about what happened here. On May 31st, 1607, about 100 men and boys set sail for the northerly destination. Discharged soldiers made up most of the colonist ranks, but shipwrights, coopers, carpenters, and a smattering of gentlemen of quality rounded them out. About 3 months later, this group landed on a wooded peninsula where the Kennebec River meets the Atlantic Ocean and began building Fort St. George. In December, with winter coming and food scarce, half of the colonists returned to England. And the next fall, after erecting several buildings, the remaining 45 sailed home. This site was ably excavated by Dr. Jeffrey Brain from the Peabody Essex Museum in Salem, Massachusetts, assisted by Dr. Pam Crane and Peter Morrison, her husband, in these excavation years, 97 to 2005, then in 2007, and then 2009 to 2013. So, you know, a little bit about the context of why this is such an important site for Maine. It is the same age as Fort James at Jamestown, but it was abandoned and really wasn't disturbed very much since that time period. It is a treasure trove. Now I want to tell you a little bit about what I am. I'm a conservator, and conservation is an interdisciplinary profession where we are concerned with the care of art and other cultural property. And we use art, history, and science as an interface. But really, I have found just about any profession can fit in conservation, from psychology when you're working with disasters, to any specific branch of engineering. I have yet to find something that doesn't lend some sort of skill to this field. There is a professional organization in the United States called the American Institute for Conservation. And I'm a fellow member, and this binds me to a code of ethics and standards of practice, which I think is very important as we deal with museums and tribal elders and cultural stewards, to make sure we safeguard the objects and also give these stewards a voice in the goal setting for the treatments. You would know conservation from painting conservation, probably in the beginning. And this work was performed by my colleague Nina Rayer of Rayer Conservation in Portland, Maine, probably 30 years ago now. This painting hung in an embalmer's studio where it was exposed to cigar smoke, cigarette smoke, and the embalming fluids, formaldehydes, which, as you see, damaged it quite a lot. And a conservator of her quality was able to mitigate some of that damage and clean it, which improves the aesthetic appeal, but also adds years of life back to an object. She also was able, and I purposefully cropped the margin where you can't see the name of this ship and you can't see the master's name. And I did that on purpose because this is a privately owned piece and I wanted to preserve their privacy. But someone had overpainted the original master's name, and Nina was able to recover that information by removing that overpaint. And also I want to point out these documentation bars on the sides here. The color bars. This is very important with conservation, that we document things before, during, and after treatment. I want to talk now about what the agents of deterioration are that we struggle with. And this is an example of a historic textile from a historic house here in Maine that sat on a mannequin in the window for years. And when you pull the lapel back, you can see that the light damaged the dies, and they're gone. That's irreversible damage. We also have the agents of relative humidity and temperature, which, as you know, work together. Too much relative humidity on something can start a mold cycle, as you see on the spines of these books that came out of a vault in one of our little towns around here, that they had a flood and they didn't know it for 10 days. And inside this vault, they had one of the original state of Maine laws, the publication of the laws when we became a state, the little blue book. So we had to save that. And of course, water is our greatest threat to objects here in Maine. This is a picture of the Fort Kent flood in 2008. Temperature works with relative humidity. When you have cycles of heating and cooling, you have an object that's swelling and shrinking if it's organic. and that's working the object. And you're going to have the surface start to spall. You'll lose paint, you'll lose wood chips. You can have an increase in the chemical reactions going on. You can have something in a moist airspace. That airspace gets cooled. All that water is going to condense on the objects in that room. And that's enough of a millimeter, less than a millimeter thickness of water to hasten corrosion cycles and the mold and this and that and the other thing. And you got to really watch the environment that an object's in. There's another kind of damage here. You can maybe read this note. It's one of my favorite notes from objects. Private property, do not open on pain of death. This means you. Signed October 1832. Well, it's got blobs all over it because this was inside a basket in an attic of a historic home that had a French nitrocellulose doll in the basket, which was overheated in the hot attic and it melted. Now, inherent vice, there's a psychological heat. You don't get death threats from objects very often, but this is kind of priceless for me. But cellulose nitrate, trinitrocellulose is TNT. And these kinds of plastics, when they degrade, can spontaneously ignite. And you've probably been aware of film footage, cellulose nitrate films or cellulose acetate films and the vinegar smell from the acetate. And when you see weeping cellulose nitrate films, you want to deal with that like right now, because that's a fire waiting to happen. So, and again, when you over and brittle, things get very cold, they become brittle, and you might have something that you tap it and now it shatters because of that. So the environment, the relative humidity, the temperature, and the light are the three big things that help us keep our objects safe. Handling something is another agent of deterioration. And you can see what happened to this candelabra that was lifted by this part and not a hand underneath to support the weight. Now, in this case, this was being evacuated from a fire. So there's a very good reason why they didn't bother. However, the damage did occur, right? Pests. Yeah, you all said, oh. So here's a historic house that has a fireplace, and the screen, I took it down because there was problems with these carpets. We traced it back to here. Dead birds had fallen down, and that attracted the dermestid beetles, which love to eat free protein, thank you. And then the bugs leave the fireplace setting and they get into the wool carpets, and now you've got a feast, and now you're losing your original objects. Flies, when flies land on your beautiful paintings that are unvarnished, or even if they are varnished, or your metals, and they take off again, they're leaving little droplets behind, and that is enzymatic and acidic, and you've got problems with spots from insects landing on your things. From another historic house that was holding pretty valuable textiles in a acidic cardboard box. Sadly, they used to have conservation staff. The staff was let go, and the mice moved in and used one of the conservation gloves as part of the nesting material, which is just heartbreaking for me to see. But this is what happens in an economy that can't, fund the right level of museum help for some of these places. Clothes moths. This is a pheromone trap where if you walked in the room, you wouldn't know that there were problems with bugs being in the room. So sometimes we test. And this is a female webbing clothes moth lure in those little blue bubbles. And the males come out. So by trapping, we're removing the mating population, but that's a lot of bugs. And we know there's an infestation in there. And then when the eggs get laid in the larval stage, they are grazing your fabrics, and they're doing irreversible damage. So in a nutshell, We use art history and science to understand an artifact through the lens of its manufacture, what's it made out of, the time period, and the culture. We consult with those artifacts, owners, curators, stewards, cultural elder, to align treatment goals. For instance, if you have a sacred object and it's got corrosion, maybe it's a statue of a Buddha, I might, as a conservator, say, oh, I want to take that corrosion down and stop that. Well, I might need to get that deconsecrated. There might be prayer scrolls up inside that sculpture that would need to be removed. And then when it's time to put it all back together, we want that to be re-blessed. Or if it's a Native American piece, maybe it's designed to fail. So maybe the only thing we can do, which respects the culture that it comes from, is to just control the environment that it's living in. Maybe we shouldn't use modern polymer adhesives. Maybe it needs to be a pitch pine. How am I going to know this if I don't have a dialogue going on with the cultural elders that this is their cultural material? So let's try to respect their needs. We also want to design our treatments to be the least intrusive as possible, and we document everything over and over again with photography, written reports. If I'm going to write a treatment proposal for a client, I may not deviate from it once it's accepted. That protects the client. And if something's discovered, we'll have a dialogue and we'll adapt it and change it so that everybody's on the same page. And I just can't go over here and use this other adhesive when I said I was going to use this one. And then I give you a written treatment report that tells you everything that I've done to an object so that you have this going forward. And in 100 years, someone can undo my work and do it better. So this is what I mean by a standard of practice and a code of ethics. And now you know what we're talking about, the Fort St. George site, and you know what a conservator is, and this is some of the fun. These are some examples of the types of Fort St. George metals that I was privileged to work on. We had iron. This is the famous caulking iron. This is copper, a bead, probably Native American. Copper alloy thing, a copper gilt, gold gilt, little tiny dangle that came from like the end of a coat or something. This is a blow up of what that is, and you see all this corrosion in here, this blue, that's indicative of copper. So immediately under the microscope, I knew it wasn't a solid gold bead. This little thimble, there was another example from St. Croix Island from 1603 from, I believe that was Samuel Champlain. What's neat about those two thimbles that they have in common is the interior is copper alloy and the exterior is iron. And working on this was like cleaning the pits on a strawberry. It was pretty fun. And then we have lead. This is a little, maybe 2.5, 3-inch high little pendant that somebody had around their neck. And this little widget again, what was it? Well, I've pulled off from Christie's auction house a similar Latin, Latten, Latin metal spoon from the 1600s. And you see the finial end. It's a seal top spoon, and that's what they had. So how do you approach working with objects? First thing, you have to know what they're made out of. So one of the things that we used was Xray Fluorescence, and you can see what the machine looks like. It's about the size of an overgrown hairdryer, and what it does is it emits a beam of electrons, hits the surface of the object, that excites a spectra, it reads the spectra, and if it has the metallurgic software package in it, it will tell you the composition. It's a point and click, and it's brilliant. If everybody wants to buy me one, see me after. So I'm going to show you 3 objects that we actually worked on and identified. And as expected, the form of this bead looked Native American to us, and the analysis is almost pure copper. 99.13% copper with a little bit of lead, a little bit of iron in it. Now, you know where Blue Hill Bay is in Maine and the town of Brooksville, there was an open copper mine there. So this could have been a locally sourced copper. We have the seal top spoon, and you can see we shot it on the side with the iron stain, and it's like 78% copper with tin, lead, iron, zinc, nickel. That is pretty much the composition of Latin metal. They put lots of metals in there together. The flat face also revealed silver and gold. So question, why? You know, is that an artifact of the testing? Is it like a fake spectra, or did they have some sort of a symbol or an emblem on the tip of that spoon that, you know, was cool, that we can't see anymore? And as expected, this little bead ended up being almost 80% copper and 15% gold. So it was neat to find out what metals were in things, and it helps us to understand what corrosion products we might be looking at, and that helps to inform what we're going to do with it. Another thing that is often done in archaeological sites is you'll get radiographs or X-ray films of your objects. And when you gang X-ray things like this, some are overexposed, some are underexposed because they're different densities. But basically, if you see solid white, it's usually a solid object. And I use a magnet to test the magnetic pole of things. But if you can see something like this nail over here on the left, and it looks like just the outline of the nail that's bright white, that was accurate. The inside is hollow. And many of the bellows nails or the nails from Fort St. George were like this, where we have a skin of the object holding the form, holding the shape, encased in a corrosion matrix, extremely difficult to get out. It's like having objects in concrete, and you have to get them out without breaking them, and they're hollow, very delicate. This is a sword hanger. We'll see this one later. You can see there's some solid outlines, but then as we go to the hook, there's no solid metal left anymore. That is corrosion holding that shape. We also, this was done by Dr. Brain. He had that done before he brought the objects to me. He also had some computer tomography done, which showed the outline of the swords that they found in the hearths for where the blacksmiths have been working. And this object here is the firing mechanism and the innards of the matchlock gun. And here it is again. And this ended up being the trigger for that gun. So I use these to help guide me when I'm starting to mechanically clean, because I have to know what's inside there. I don't want to remove something that is real object, or it's only corrosion of the real object. So I got to be real careful. And also we can use scientific methodologies. This is FTIR, which is Fourier transform infrared microscopy. Jeffrey had the idea that this was possibly part of the bellows, and we wanted to test that. So we sent it out for this analysis, and they targeted a little bit of the blue, and that came back as Prussian blue with a date of 1704 to 1710 by when it started to become a pigment and available. So this is outside of our time period. He also backed that up with another analysis that put it into the late 1800s. So this is something that is not from the Fort St. George site, but it was an inclusion in the site. So now I have my scientific analyses, I've got my radiographs, and now I want to start cleaning. I want to start with bamboo skewers, and I'll sharpen them up because bamboo is going to be softer than my metal. I don't want to scratch anything. And if this is not good enough, then I get brave and I start with my scalpels. And I use a stereo microscope so that I can see the object really well. And I'm cleaning with lots of different blades. If that's not enough, I use this machine, which is a glove box, put my hands inside with the object, and I use my stereoscope over the top. This is a glass lid. I have an air compressor hose that comes to this machine, and I have a vacuum cleaner with a HEPA filter to evacuate the dusts. And this is a mini sandblaster, basically. And I can control how much powder and what types of powder that I'm shooting at things. And I can also control how much PSI I'm shooting something at. And I'm watching really carefully under the microscope so I can see exactly what I'm doing. I also use this pneumatic air compressor driven tool, which is a paleo tool. That's a vibrating needle, and I can take 1 grain of sand off at a time. So I have raccoon eyes all the time from staring through my microscopes. So mechanical cleaning is one thing, but we also use chemistry quite a bit. And chemistry is as close to magic as you're going to find in this world. Particularly when you think about metals. This site was blessed that if you're in that parking lot and you're looking out to the water, on the right-hand side was a bog. And in the bog was limonite, which was bog iron. This is something that they could scoop up and they could take into their furnace. They could heat it up with extra oxygen, with charcoal. I want to cycle back to the charcoal in a minute. And they can actually extract iron from the ore. Now, iron is not happy being extracted, which is why anytime you have an iron object with moisture and the right heat, it's going to run off and rust, right? It's more stable when it's alloyed or combined with other elements. Doesn't like to be by itself. So Dr. Brain found the hearths, and actually you probably can't see it, but I'll just tell you that right here is where the trigger was for the matchlock gun, and the swords were found around this particular hearth. Going back to charcoal, that Smithsonian magazine referenced that they had skilled laborers with them, and charcoalers were a very important skill in England that they brought with them. And in order to make charcoal, they really want to have a white oak, and they want to have 6 months to dry it. And then they're going to slowly burn it in a way that reduces it to charcoal. So they had to wait until they could produce that. And so they're postulating that in the spring of 1608 is when these furnaces were going. And he did send out to 2 different people. They analyzed the slags, which is the glassy material that's left over from when you smelt iron out. And also he analyzed the charcoal, and it was oak charcoals with a little bit of birch. Sometimes artifacts are gone. And I have to credit, I don't know who found this, but a sharp-eyed archaeologist on that site, or one of the very capable volunteers which worked with Jeffrey for seasons upon seasons. These are highly skilled people. Found this very ephemeral, almost 2 centimeter wide little chunk, looks like corrosion. This is the impression of plain weave cloth that is only held in the corrosion layer. So that's a very, very fine weave, fine fabric, and it's only held because this iron piece corroded next to it. So in a salty coastal soil, you have salt, you have moisture, you've got iron, you're going to have a galvanic corrosion cycle happen. So your iron is, the salt and the water become your electrolyte. The pure iron is starting to give up itself, and it's grabbing shells and sand and sticks and other things that are near it, and it makes this concrete-like corrosion product, and that's what they bring to me. I have to reverse that. So I'm going to use on objects that have good magnetic pull. I know there's a lot of metal left. I'll make a bath, use some sort of electrolyte, sodium hydroxide or sodium carbonate, and I will make the object negative, and I will have these sacrificial plates inside with a solution that drives electrons back out. And I will electrolytically reduce that corrosion product, and it drives the chloride ions out. And so this machine will measure the concentration of salt that I'm evolving, and it makes porosity in that corrosion layer, and then I can actually start cleaning it off. Sometimes it just kind of falls off on its own, which that's the nice way to do it. But it can be quite a struggle to work with concreted material. I missed one. There we go. This one is another type of reduction. It's alkaline sulfite reduction. So basically I have a jacketed water bath, and I have a container in the water, and this is a fish aquarium that heats it up, a heater. And inside the box, I have, again, water, and inside the Ziploc bags, I have my treatment solution, so I can individually treat objects, but I can do it as a gang at one time. And I can monitor the chloride evolution, and I can watch. You can see this one is doing really nicely. It's evolving, and the corrosion is coming off the iron piece. Again, for only objects that are in pretty good shape. I have an undergraduate degree in art, and then my master's degree is science. So I want to just do a little shout out about art in our field. And, you know, when you take a photograph of something, that's one style of documentation, but an artist's eye can subtract information that is obscuring and can pull out salient details and make that much more clear for people, and as it's another way to document things. So that's an example of this kind of thing, where I was able to draw the faces of this hewing axe and articulate that. But also, I'm going to get a bag of objects that look like that, and I have to figure out how they are related to each other, and what is it? I don't know what it is. So I have to sit there and study it, and I can't clean anything until I know how it goes together. Because if I clean it, I'm going to change soil on this piece that matches soil on this piece, and maybe that's the only clue I get, that these two belong together. I may not have beautiful edges that line up all the way, but I might be able to see by the topography of the corrosion that this thing that's this thick goes at this end, and this thing is, you know, you get the idea. So you have to sit at your bench and you have to draw these things, and you have to mess with it until you figure out a pattern as to how they go together. My son, Aiden, is very, very spatially gifted. And when it comes time to mending things as a little boy, I wouldn't let him touch a thing, but I would bring him down and say, okay, how's it go? And so he could flip shapes around in his head and help me figure out how to put together pottery and things like that. I want to point out these little notches right here, and then tell you what we actually are seeing. This is a piece of armor. It's a lame. It's one of the sort of the bands in a piece of armor. And it has a leather strap that's been riveted to it that's only held in the corrosion. And these little holes are actually where they diamond shape pierced it. And that's where the tang of the buckle would have gone through. And so I drew it part way, and then you can see this part here. You can see it better up here. That's the actual buckle with the tang. The tang is the little thing that, you know, you put through the holes. And then this is what it kind of would have looked like had it not been like stepped on and broken. So using art to help figure out what you have is good. And then of course, how far do you take this in cleaning? This is a leather strap only held in corrosion. I can't clean that, but I can define what it was. I can work with this. This is another lame, and I am postulating in this picture that somehow maybe they went together, or maybe, I know this is a lame, I know that's a lame. I don't know where on the piece of armor they went, but we put it all together there. And here's the matchlock mechanism. And this is, again, just starting to figure out, how do you get into something like this? It'll be easier to show you the whole sequence with this sword hanger. This beautiful curved gooseneck kind of thing. This is what it looked like when it came to me. This is what Jeffrey brought me for an X-ray. This is partially cleaned. This is when it was all done, because as you can see right here, this is the shape. It's hollow on the inside. The neck is hollow. This is hollow. And then it pretty much is just a prayer held together by corrosion. And Jeffrey found how a sword hanger is actually used. And so here's one, here's the hook, here's your leather straps, and it goes around your sword, and you hook that hook on your sash, your belt. And I was able to go down to James Fort in 2019, and lo and behold, look, they have an identical one to ours right there. So that was pretty fun to find. Surprises. Here's a lump of corroded metal that had a very strong magnetic signature, and it turned out to be a tiny cylindrical lock made of iron. Now, I don't know how they would have opened this thing. It's riveted here and here. I could find no key, no way, no piercing to push a button to release a catch. There is a break, I think it's right here in it. I don't know if it would have rotated open and shut like that, but it's a mystery, but it was really cool to find. Here are the swords before treatment, again, because they're so messed up and they're 400 years almost, old. I could define the edges. I could show you the tang. I could stabilize it chemically, but it's not very pretty. But remember, the blacksmith was breaking these things up to melt down. He found another sword, and in another bag, I found this indescriptive lump that happened to be the same size. So that's where the artist's eye said, I remember that kind of thing. It was about that big. I'm going to bring it over here and see if it fit, and it fit beautifully. So there's another piece of that sword that he had broken off. This lump turned into a sword pommel, which is the balance of it above the handle to counterbalance the weight of the blade. So we had that. And then the matchlock firing mechanism. This is a matchlock gun. And you can see that here's the trigger. It's this long rod. And when you pull it up, it makes the serpentine come down, and it's holding on to this burning match. And it goes into the pan of black powder, and then kaboom, your gun goes off. This is what our piece looked like. And of course, we used all kinds of radiology on this one. Just what can we see and how do you get into it? And this is what it ended up being after I was able to get all the corrosion off of it and find the pieces of it. And then right here is a place that had where the threaded rod for the trigger would have gone in. So that's the trigger. This is actually screw threads right here, which is pretty fun to see. This is a giant corrosion blister that I could not open because it went so far on the inside that I was afraid I would lose the form with those screws. So sometimes enough is enough. Just don't overdo it. And this is how it came to me from the field. This is probably wrong as how it's put together, but I think this is probably going the wrong way. This was early on when I was fussing with it. But these are all the pieces together. In another bag of slag, I found this piece, and then I found another piece that went on the tip here. Again, the blacksmith was breaking this thing up. Now to talk about the lead. This, when you have an object that absolutely relates to a human, it's a pretty special moment. when I took the corrosion products off of this, I want to draw your eye to the tip where the tooth marks of the guy who owned it used to bite on it. You know, and it's like, what was going on? Why were you biting lead? But, you know, here you go. That's very ephemeral. That's a human right there. Another thing, Jeffrey found a couple of, or Jeffrey and his team found a couple of Bale seals. And a Bale seal is something that they would have, it's two lumps of metal connected by a little handle, and you pinched it over the end of a bolt of cloth, and it would have identified the kind of cloth or the dye, like madder woad. This is an example of a madder woad open weave icon. It's the bag that they would have put the fabric in, then put it in the woad, which is the blue. It's before we started using indigo. Madder gives you a red, woad gives you blue. The ancient Celts were called woads because they did the blue on their faces and stuff. So this Bale seal, I think it actually had been found before his excavations, maybe in the 60s. Somebody put a coating on it, which was doing nasty things to the surface. I was trying to get the coating off. I put it into a solution and I turned around and all this blue is coming into the solution. And I fished it out and I had my camera right there and I photographed it. And then before my eyes, all that blue disappeared. And the little chem wipe that I used to like pat it dry had blue on it, that disappeared too. This is the only evidence that I have that happened. I'm like, what happened? This is lead, it should not be doing this. This is the side view of it, and that's textile inside there. And there's textile fibers, and the chemical I used solubilized the dye from the woad, and there it is. You get some nice gifts sometimes from objects. Another object that's kind of fun, this is the Hans Crawwinkle Chaton that they found. Chatons are counting pieces, and they go way back, 1500s. And in Nuremberg, Germany, they had a whole racket where they were making these in this family, the Crawwinkle family, who when his father did it, and then when he died, Hans II got to make them. And they started to have the use of them not only as game pieces, but they were counters. Before people would write Arabic numbers and do mathematics, they would lay out a grid where you have 5 lines and you put these counters on the lines or in between the lines. If it's on the first line, that's 1. If you add a 1 to the space in between, now you've made the number 6. And if you want to know how you do addition and subtraction, just get this book, 1769, Thomas Snelling. He will tell you everything you ever wanted to know with examples in Roman numerals of how you can do mathematical sums. So here we have one. But one of the fun things about these things is that they started putting these little slogans on them and his name. So this one says on the obverse, which is the front, Hans Crawwinkle in Nuremberg. And this is a type of German, High German, or maybe it's not high, but it's a sort of type of German that takes shortcuts with its spelling. And it has a rose in the center and the crowns and the fleur-de-lis. And then on the other side, it's this thing, a Reichschapelle. And it has this shape with a globe in the middle here and a little cross. And it says, Verbum Domini manet in etern. The word of God remains eternal. So this was kind of a fun piece to work on. And as you can see, it came to us without full integrity and it was corroding really badly. This one we sent to the scanning electron microscope lab up at Global Bryant Science Center at Orono, University of Maine. And this is an example of what a SCM microprobe printout is, where they're sampling. They give you an average of the different metals And it turns out to be almost 80% copper, almost 20% zinc, with trace metals in there. And, you know, this was common. This is an example of a metallurgic cross-section of a tiny fragment of that thing. And this is the corrosion crust. This is the real metal, and it's an alpha-phased metal, which just means that all of the zinc dissolved into the copper. Later on, when you get into like Muntz metal, Nathan knows because we did a paper on this, Muntz metal could be 70% copper, 30% zinc, or 60-40 was the original formula, and that gives you a second phase here, and you can actually see it in a metallurgic cross-section. And it's not as strong as a metal like this, which only has one phase. So that's a bit about the metals, and I wanted to talk a little bit now about one of my favorite pieces, and this is how I got into this site, is because in 2005, which I think was going to be the last year, and this was in the last couple days of the last excavation, of course, they find like the artifact, which is from the storeroom. It was in a wet corner of the site, and this is a post. And it's not just any post, it was a post that still had some of the bark on it and the colonists' tool marks. So from when they cut it down. So that was pretty neat, tangible connection to these men who'd been working so hard to build this fort. And when you think about wood, we've got loosely two kinds. You've got the conifers, which are the gymnosperms. They have their seeds that are naked, needle-like leaves. And then you have things like apple trees and cherries and oaks that are the angiosperms. They're the hardwoods, and their seeds are within a fleshy ovary. This, we're going to find out a little bit, how do you identify wood? Well, I'm trained in this. You use the cross section and then the radial section and a tangential section. And if you're trained to know what the cells look like, you can usually key this out if the wood has integrity. So you use those three planes. This is a cube of eastern white pine, Pinus strobus. And if you take this little cube and you blow it up in a scanning electron microscope, you're looking at the cells line up beautifully on top of each other in nice straight rows. This is a resin canal. This is the radial face. So if I jump down here to the radial face, I've got these longitudinal members and the rays where they cross. That is a cross field pitting place. And in softwoods, it's incredibly diagnostic. And that's a window pit. If you go from there to here, that means it's a white pine, basically. And if you miss this resin canal, because maybe I only sampled it over here, if I go to the tangential section and I look, oh, there's a fusiform ray. That's a little resin canal. And that lets me know, it's a backup that I know that I've got the kind of wood that I think I do. This is a gradual transition, and you can see it here blown up. It's growing. Oh, the light's fading in the fall. The tree's getting sleepy. Up, went to sleep. Then in the spring, the light levels are high. The hormones and auxins rise, and the tree wakes up, and now it starts putting on the wood again. Softwoods will do that in nice, beautiful rows. Hardwoods came later in evolution, and the jobs differentiated for the cells, and they have much more cellular types of cells, and it's really pretty. It looks like lace under the microscope. This is abrupt transition where it was growing, and oh, it's done, and it's going to wake up in the spring. Our wood was like that. It was an abrupt transition softwood. And here are some you just take a razor blade so you don't get beautiful clean slides, but this lets me know that it was a abrupt transition softwood. This let me know it had resin canals, because there it is. This was pinoid pitting right here, and all of that together. That post came from the southern yellow pine group, which goes from pitch pine here in Maine all the way down to Florida. And we also had bark that was still attached. And so we had the pith, which is the center of the tree, all the way out to the bark, and that was 95 growth rings, which lets us know that that wood began growing in 1512. So now, how do you deal with a wet, waterlogged 90-pound piece of wood that the surface is so fragile that if I touch it with my hands, I'm going to spall that really decayed surface of 1.5 inches deep off? We couldn't touch it. So we photographed it through water with scales floating in the water. Then I cut down the container that it was in. We photographed it again in air. I was able to put that container in here. I used my chemistry to, what I want to do is I want to replace the water in the cells with a chemical to give it support. And I used polyethylene glycol. And I did this over time, and I changed the solution strength. And what I'm doing now is I'm taking it out so I can add more chemical. And then I'm going to carefully put it back in because I'm not moving that piece as little as possible until it has soaked up as much as I thought it could for the next phase. And this was around Thanksgiving, and it looked like a turkey sitting on my lab bench. And then I put it in my freeze dryer. And a freeze dryer is a machine that has a compressor that lowers the temperature here to about -40 centigrade. And it will also have at the bottom another compressor to this place. And then there's a vacuum pump. When you put a vacuum on, oops, go back. Well, I'll just tell you. So when you put it in, that thing sat for 2 months in the freeze dryer, and it slowly dried. And the reason I needed to do that is that when you think of a fragile cell and water or liquid in it, if you pull that out, it's going to collapse the cell. So I want it to go from a frozen, like a couple of millimeters thick of water to the gas. I want to sublimate it and avoid that liquid sucking motion. And so that's what this machine did. And I think we took 30 some pounds of water out of it. And then eventually it equilibrated. And then I was able to show you now what the original tool marks look like. This is the end where we've got, adze marks, and I'm not sure exactly what did this, but we've got it. And we were able to save all the pieces of it. And we also had the bark. This is, I don't think they found any wood at James Fort in Jamestown. This is the best of the several stumps that they did find for the storeroom, but this one is the one with the money because it had the marks on it. And this is where it was on exhibit at the State Museum. So now, my 3 takeaways. Please support your local archaeologists, for they does work in long hours for little pay. And if you are someone who's interested in doing some archaeology, you can join the Maine Archaeological Society and you can volunteer for a dig. And I hope that I have shared a little understanding about what kind of information you can find from an archaeological site, and particularly with science, and a little bit of a behind the scenes view of what the life of a conservator is. If you need a conservator, you can go to the American Institute for Conservation's website, and they have a find a conservator tool if you need a paintings conservator or a paper conservator. Good stuff. So now that is the end of my talk. You've been awesome. Thank you so much. There's a question. Go ahead.
The X-rays of the pieces, the ones that were hollow, the X-rays that were hollow, is that because the metal had like disintegrated over time, or it was?
Yeah.
Okay, so it wasn't like they were created hollow.
No.
Okay.
No, that's where that galvanic corrosion cycle happened. So the iron from the interior went out to make the concrete-like material surrounding it, like galvanic corrosion. Yeah. Mr. Stevens? How does what happen?
How in the world does the iron inside the nail come out, leaving the outside of the nail?
It's a galvanic corrosion cycle, and I don't know exactly, honestly, how that happens, why you have it a hollow in the interior, but this site, this is the worst condition iron I've worked on, and it was constant throughout the site. It's soft. This is soft iron. And there's probably some kind of wonderful chemical modeling with electrochemistry that would answer that question, but I can't answer that one specifically.
Do you assume it was chloride ions that was?
There's definitely chloride ions in that soil. In fact, they're a pit corrosion. So if you had a piece of iron and chloride is here, the chloride is the cell and it helps to begin that corrosion cycle. And what happens is iron moves and it will make a collar around that, and then it'll close off and it'll be a blister. And the question always is, if this is the surface of your object, do you want to leave it all with the raised bumps? Is that the better look? Do you want to excavate that out? And now you've got pocks, but also you've been able to do something and relieve that chloride ion, like you can soak it out, or at least reduce it. And it just depends on the fragility. Like if it's an inscription, you may not want to put a hole in it. You may not want to take stuff away from that. No.
Thank you.
Yeah.
We have one from Zoom.
We have one from Zoom.
There's a question, where can these objects be seen?
Right now, you can't see them because the Maine State Museum is closed, having an asbestos removal problem. But when the museum is open again, there was a permanent exhibit on the Fort St. George objects, and you can see them there. That's in Augusta, Maine. Maybe in 3 years. Yeah. Yes.
I know that oops. I know with, for example, the Viking ships where you have lap straight planking. And so when you conserve plank, you can tell if you've done it right because your holes will line.
From what I understand, there was a squared part and then kind of squared and then it was rounded. And the bottom of that post was beveled, so it wouldn't sit exactly flat. Some of it was flat and then there was a thing that went up like this. And I don't remember if the flat part was inside the building or outside the building, but the archaeologists know that, and they would be able to tell you that. I'm just concerned with the material science of it. How do I conserve it so that I can preserve those tool marks? They're interpreting it, and we have dialogues back and forth. You know, if I don't understand how an object is working, I would have consult with them, and that was really very useful. Yeah, but I'm not an archaeologist, even though people think I am. I am not. I just speak their language a little bit. Yes.
Early on in your talk, you showed some pictures of objects that had been conserved, and you had color-coded little patches.
Yeah, those are Kodak color scales, so that we can, those are known reference standards, so that we can adjust the color of the photograph of the object by referencing that colored patch. It's part of the documentation.
Thank you.
Thank you. Well, I would like to thank some people, my family, Sean, Maeve, and Aiden Carlson, for family support when I did this work. Jeffrey Brain, Pam Crane, Peter Morrison for the archaeological information and the dialogue that we had about a lot with Pam and Peter about lead. The Maine State Museum for financial support, and of course for the Maine First Ship for inviting me here to tell the story. Thank you all for coming. Have a nice night.